So let's get started with today's material. Last day of class, again, sad, but it's still good because it means we are moving on to bigger and greater things. When by that I mean the fall semester, which involves a lot more classes. Anyway, last week I was not able to finish our talk on regression. I mentioned that we had a couple more things to talk about, and one of those was the coefficient of determination, right, which we've already introduced as the residual coefficient. So my coefficient of determination, also introduced as the residual coefficient. Which a lot of you have already seen this coefficient, right? And this is the infamous or famous R squared coefficient. We already said in the last class that R squared was determined by taking 1 minus the ratio of the sum of squares. So 1 minus the ratio of the sum of the error sum of squares to the total sum of squares. Now, a couple of things you want to keep in mind, and some interesting things about the residual coefficient here. If x and y are jointly distributed random variables, remember that when random variables correspond to a joint probability distribution, we have a couple of coefficients, such as the covariance and the correlation. So if x and y are jointly distributed random variables, then this R squared value is actually going to be the square of the correlation coefficient. So if you can find the correlation coefficient and you square it, you're actually going to end up with the R squared value for your line fit, assuming you did your line fit correctly. If we analyze these values, then we know that this ratio is going to be a number between 0 and 1. And what that means is that my R squared value is also a number between 0 and 1. We typically define R squared as the amount of variability in the data that can be accounted for in our model. In other words, whenever we study statistics, we use statistics to study variability. And when I say variability, what that means is, well, values that have different, or I guess properties that have different values, even though we repeat the conditions, we try to keep the environment the same. So in our model, if we can account for most of the variability, which means that if our model, let's say, is a linear regression model with only one variable, one independent variable, and it turns out that the physical situation only exhibits change from one independent variable, that means that R squared will be higher because the model accounts for most of the variability of the data. However, if we have more than one variable, for example, let's say that we're trying to figure out perhaps the evaporation rate of a liquid. Now, if we're thinking of evaporation, you may consider that the variable you want to measure is temperature. Yeah, you think, for example, water after a certain temperature begins to evaporate. So perhaps we can figure out a correlation between temperature, maybe ambient temperature, and then the evaporation rate of a liquid. However, we also know that evaporation is not just about temperature. It has a lot to do with pressure as well, specifically the ambient pressure. Beyond that, we need to consider things such as the humidity of the ambient, as well as the vapor pressure of the liquid. So there are many variables that influence the evaporation rate of a liquid. However, perhaps we come up with a linear regression equation that gives us the relationship between the temperature and the evaporation coefficient. My R squared value will tell me how much of that variability are we able to consider in the model. However, because we are not looking into other variables such as pressure, ambient humidity, and vapor pressure, then perhaps the amount of variability that we're able to consider is going to be very small. Okay? If you want numbers, you deal with numbers. An R-squared value of 0.877 means that the model accounts for 87.7% of the variability in the data. Found a typo in the notes. And if that's the case, then the closer R-squared is to 1, then the more variability, right, we should be able to account for. If you think of it, R-squared very, very close to 1 means that we are accounting for very, very close to 100% of the variability in the data. Now, I want to be careful with my wording here. In fact, in the notes, I put quotation marks next to where I said the better the model is, because there is such a thing as a bad model with a really good R-squared value. So we're going to talk about this later in this class. So keep in mind, a high R-squared value tells you that your model accounts for a lot of variability in the data. Whether or not that means that the model is better or the best really depends on what it is you're measuring and how you're measuring it. So I don't want you to fall in the trap of thinking that as long as you create a regression model, as long as your R-squared is close to 1, that somehow that means your model is good. It may actually not mean that, but we'll talk about that later. I like how in this class, every time I give a definition or some statement or some rule, I always say, well, it's actually not really like that. We got to be careful. But that is the general gist of statistics. One thing we understand is that linear regression allows us to estimate observations based on a sample. If we were to collect data and graph that data, I don't like that we have a new pen, and for some reason, it's really, really, really hard to write with this new pen. It just makes me want to go back to my old pen. Much better. So let's say I am collecting some data, and from that data, I can put together a linear regression equation. Perhaps my linear regression model looks something like this. What this model allows me to do is to estimate, right? Estimate the mean value of data within my range, right? So essentially it allows me to, and I want to be careful with my wording here, it allows me to interpolate, if we use a very crude definition of interpolation, right? It allows me to estimate where my values could fall if my independent variable was a certain value that's within my sample data set. But now I would like to ask a different question. So we know that our regression equations allow us to estimate values when they are pretty much within our data set. But could we use linear regression or any regression? Could we use any form of regression analysis instead of to estimate existing values? Could we use it to predict future values? Because this data comes from experiments that have already taken place. Because these experiments have already taken place, then for sure we will be confident of how close our model will be to reality. But could we use this model then to estimate data points that have not taken place yet? For example, let's say that we don't really have a measure for this specific value of X. We don't really have a point there. Could we perhaps use this linear regression model in order to estimate the location or the magnitude of that unknown point X? What do you think? Are we able to do that, or are we not able to do that? It looks like we should be able to do that according to the chat. And that kind of makes sense because the whole point of creating this model is so that we can use it later. And we can't really use the model if we're limited to the data set that we have. If that's the case, we only use our data sets. So the question stands, can we use this to predict future observations? The short answer is yes. The long answer is yes, but. There's always a but, right? Yes, but we need to be careful how we actually apply, right, that prediction, our model to those predictions. Let me share a graph with you from one of my books. This is a graph that considers son's heights in inches versus father's heights also in inches. Let me tell you what this is about. The main idea behind this graph comes from Francis Galton. We already talked about Galton before. He collected this data and he plotted it. Before I talk to you about his intentions in collecting this data, let's see if we can draw some conclusions from this graph. If we look at this graph, what does this tell us? What can we say about this graph? And by the way, just to give you some remarks, the points are the collected data sets, and then this thick dark line is our regression model. This dashed line is essentially a 50-50 model. It's simply a line at 45 degrees angle. That's all it is. It's a line that says for 65, we have 65. It's just so that we can see how the regression line differs from a line that shows like a 45-degree angle, essentially. That shows perfect correlation. So what can we draw? What conclusions can we draw from this graph? Any ideas? Just looking at this graph, you have son's height, father's height. So Ramtin says in the chat, the taller the father is, the taller the son will be according to the regression line. I want to be careful with the wording here, Ramtin. I would rephrase your answer to say, the taller the father is, the taller the son is, because this is data that already exists, right? So we are collecting that data. Now, if we were to use that regression line to predict, then yes, Ramtin's statement does have the correct wording, because we could say, well, we can predict that the taller a father will be, the taller the son will be according to regression line. I think you're at a good point, Ramtin, but I think there's more that we can see from this data set. In the chat, Renee says that the middle has more data. It seems that most of our data points kind of fall within an average range. That's correct. That's also right. We do see, and this is similar, right, to the concept of regression to the mean, right? We see that most of observations are kind of like within a central value, also central in the theorem. And then the extremes, of course, are actually less recurrent. Good. Any other conclusions? We've already made some conclusions about the direction of that line, of the regression line. Perhaps we can try to draw some conclusions from the slope of that line relative to the dotted line. What conclusions do you think we can draw from that slope? Any ideas? It seems that shorter fathers are not making taller sons. Now, I want to be careful with that. I think I understand what you're saying. However, let's look at the regression line and see what this tells us. First of all, I don't really know what tall means. But assuming that tall is some objectively visible value here, let's look at this line. If my regression line were to follow this 45-degree angle, what that means is that a father that measures 65 inches in height is expected to have a son that measures 65 inches in height. That's what we're expecting to see if the line followed a 45-degree angle, but it doesn't. It follows a different angle, a different slope. And what do you think that slope tells us? Christian says the fact that the slope is less than 1 means that generally the sons are shorter than their fathers. You could try to come up with that conclusion, but is that really what the data is showing us? Let's just plot some values here. Let me just draw some nice little values, and let's see if what Christian is saying actually holds true or not. Let's say, and let's use our regression line as our base, as our estimator. Let's say that a father's height is 65 inches. So I'm just going to draw a nice little vertical line up here. Let me make it a little bit more noticeable. So if a father's height is 65 inches, then what is the expected height of the son based on this regression line? Well, we go to 65 inches and we draw a straight line to the left. It seems that the expected height of the son is actually a little bit more than 65 inches. In fact, this slope tells us that at a certain value, sons' heights will be greater than fathers' heights. However, Michael says it right correctly. What happens when we get to the 45-degree line? Well, at that 45-degree line, you can see that it is expected that the father's height and the son's height will be pretty much the same, which is about 70 inches. Just make this line a little bit more noticeable. A little bit less. And then beyond the 45-degree line, because remember, it's a 45-degree line, so what a 45-degree line tells me is essentially that x equals y. But beyond that 45-degree line, we actually see something different. So now let's say, what happens if a father is 75 inches tall, for example? Again, I'm going to try to draw a vertical. Let's make it a little bit more noticeable. It seems that beyond that 45-degree line, a 75-inch tall father is expected to have a son that's actually less than 75 inches tall. So what is this telling me? Right? It seems that we do have some type of correlation below a certain point, and then a different type of correlation above a certain point. So in the chat, Renee says the same thing. The upper part of the regression line is opposite. So 75 inches tall fathers have shorter kids. That's correct. So what this line is telling me, right, and this is something that Christian mentioned in the chat, what this line is telling me is that it seems like sons' heights are going to try to average out. So what Galton concludes is that, well, shorter fathers have taller sons, taller fathers have shorter sons. In fact, it seems like the height of the sons seems to be regressing to the mean. That's what we talked about earlier, called regression to the mean. Galton called it regression to mediocrity. But given today's connotations, we just call it regression to the mean. This is actually also true for mothers and daughters. So if a father is very, very tall, can he be expected to have a very, very tall kid? Well, very, very tall son? Well, not quite. And of course, this is very, very general. So Rantin mentions we should also remember that fathers are not the only factor in determining a son's height, and that's absolutely right. Interestingly, though, this phenomenon applies to any population group you study. It also applies to mothers with daughters as well. So it's a pretty interesting phenomenon, but it does show a nice way, a nice concrete or a conceptual way of looking at how regression to the mean works. In fact that this slope is less than 1 proves regression to the mean. It proves that smaller values will be correlated to larger values, and larger values on one side will be correlated to smaller values on the other. So the fact that the slope is less than 1 shows regression to the mean. Christian asks, is there a correlation between fathers and daughters and mothers and sons? I do not know, but that'd be something very interesting for you to check out. I think it'd be really interesting to know. Now, the concept of regression to the mean is the same reasoning that we're using in our regression analysis, right? If our data does exhibit, if our data do exhibit a regression to the mean, our regression analysis, right, which is what provides us a mean of the data, should be appropriate. Now, the question stands again. Does this allow us to accurately predict future observations? Now, the word here, the key word here is accurately. Well, no, because if we just take our regression line, it only gives us a mean, right? An average, a mean. I'm not going to use average, a mean value. But the real data, the real values are actually scattered. So we do need to use a little bit more than just our regression line to be able to predict values. Now, if that's the case, you may wonder, what is this regression analysis good for if we can't really use it to predict data? This is a question I had when I was first trying to put together some data in my PhD. I was thinking, well, our data is very scattered, it's very varied, and there seems to be a lot of factors that are going to affect it, right? When you work on experiments that have a lot to do with behavioral stuff, such as with mammal behaviors, it seems that mammal behavior is very varied. I mean, we can assume that they only act on instinct and that you can accurately predict what an animal will do, but anybody that has pets, more than one pet, knows that no two animals are the same. So I think when we're trying to do behavioral studies on animals, what good is it to try to fit lines and curves into my data if that is not going to actually predict an observation? So I'd like to propose another way of looking at regression analysis. Instead of looking at regression analysis as a way for you to predict values, we should instead use regression analysis as a way for us to predict patterns. So whereas I don't think it's smart to say or to use regression analysis to say that if a father is 65 inches tall, so 5'5", the son is going to be 68 inches tall. Maybe that's not what I want to say, right? Because I could try to come up to that conclusion. My father is 5'5", and I am 69 inches tall, so 5'9". So there is a little bit of truth to that, but it doesn't really work the same way for everyone. However, we can use this data to talk about the overall pattern of the relationship between fathers and sons' height. In other words, we use this data to say shorter fathers will tend to have taller sons, taller fathers will tend to have shorter sons. So whereas we don't really use it to get one specific point, we can use it to get a relationship between multiple points. And that is what the behavior analysis I've been doing is for as well. It's not really to predict the accurate mechanics and behavior of one animal per se. It's actually to predict patterns. So if you change this variable, how does the overall pattern of your mammals change? So the idea behind regression analysis is not to predict specific accurate values. It is to predict patterns within our data and within our population. So I will say, yes, we can use regression analysis to predict patterns for future observations. Now, of course, there are many ways to be right with regression models, and we talked about how to come up with a regression model, how to calculate a linear regression equation. But we should also talk about all the ways that we can be wrong with these regression models. Whenever you say that your data lines up with your model or that your model is the best fit, you are making a lot of claims about not just your data and not just your methodology, but the general philosophy behind regression. So you want to be careful about making those claims, especially in industry or in scientific pursuits. I'd like to talk about some examples on how to be wrong with regression models. First off, R squared, we already said that R squared is a measure of the variability, of the amount of variability taken into account by your model. So if your model considers one variable, you may have an R squared value, let's say temperature. However, in the case of evaporation, if we want to add another variable to the model, so let's say we're doing a nice little curve where our equation, our regression equation, consists of two variables, temperature and pressure. Because we are taking into account one more variable, so we're taking into account the variability induced by pressure, our R squared value is going to increase. In fact, if we take any model and we just keep adding variables to it, we will be increasing our R squared, regardless of whether or not those variables are in fact functioning the way we think they function. So we can take a model and we can add as many variables as we want to increase R squared to very, very close to 1. And we may think to ourselves, yes, this is a good model. This is the best fit. However, just because we are increasing R squared to 1 doesn't mean that our new model is better. In fact, we're going to have to see if the error sum of squares of your new model is actually reduced, right? Because if you increase your R squared, but your error sum of squares actually is not reduced, at least by an amount equal to the original error mean square, then we're actually making our model worse. Now there are different examples we could use to look at this, but I think something like this is actually better illustrated if we talk about polynomial fits. So in my fluids lab class, in the first experiment, I asked students to put together some data regarding temperature and viscosity. Maybe it may not look like this. It may look a little bit weirder. And I asked them to fit a polynomial curve um, to determine the relationship between the temperature of a fluid and the percent error that the equipment, the viscometer, ends up having. So that is what we have to do in our fluids lab. And I usually let students decide on their own what order of the polynomial line they want to choose. Some students choose a first order line, a first order polynomial equation, which essentially is just a line. Other students choose a second order polynomial equation, which will be, well, some sort of curve. Other students may choose a third order, a fourth order, a fifth order, and so on. However, if we think about how regression works, if we increase the order, then we are essentially adding more curves to this line to make it closer to our values. That's what we're doing when we're increasing the order, right? If we increase the order to a third order, perhaps we're going to add a curve here and a curve here so that my line is closer to my points. Generally, our order, right, will determine the curves, the number of curves that our data has. Generally, not completely exactly. If we set our order to be equal to the amount of data points we have, then what we're going to produce is a curve that passes through all of our data points, a curve like this. And if we calculate the R squared value for a curve like that, a curve that passes through all of our data points, if it passes through all of our data points, then you know that there is no error sum of squares because the value minus the regression value is 0. So 1 minus 0 is just 1. So if we increase our polynomial equation, our polynomial order, such that my curve passes through every single point, what is the R squared value for this curve? If we increase our order such that the curve passes through every single point in my data set, what's the R squared value? 1, correct. You don't have to know anything about fluids, but does this graph look realistic? Does this graph look like it can accurately model or it can accurately predict the relationship between temperature and error? It does not, correct. In fact, it doesn't even allow me to come up with a pattern. What we see here is that our pattern increases and decreases in slope with every observation. So we can't even come up with a general pattern to say, well, the more temperature, the less error or the more error. Whereas these lines do allow us to come up with a pattern and say, error seems to be higher at lower temperatures. There are exceptions, of course, but in general, error seems to decrease as the temperature increases. However, our nice polynomial equation with an R squared equal to 1 does not actually reflect that. You may be surprised, but I do get submissions that select a polynomial order equal to the number of data points. I think it's 10 data points, so they come up with a 10th order polynomial equation. And yeah, and you can't really draw conclusions from that, right? You can't draw any conclusions from that. All right, so there are ways to be wrong when doing regression analysis, and want to make sure that we are careful of those ways. Other than that, regression analysis, don't be discouraged. It's still a very helpful tool to identify these patterns. And you'll have some chance in the final exam to show that you know how to do a regression analysis.